Welcome to Pod Talk. Today we're exploring the sidecar logging pattern, one of the most powerful operational patterns in Kubernetes. We're going to break down exactly how colocated containers collaborate through shared storage and why this pattern is essential for production deployments. Let's start with the fundamental question: why does the sidecar pattern even exist? First, learn the why. Kubernetes wasn't built just to run containers. It was built to solve complex operational problems at scale. Problems like deployments, scaling, health monitoring, and most importantly, keeping your infrastructure manageable as it grows. The sidecar pattern embodies a principle that's tested on the Certified Kubernetes Administrator exam: separation of concerns. This isn't just an academic concept. It's how production systems stay maintainable. Here's the core idea. Your application container should focus on one thing: your business logic. Serving web traffic, processing data, handling API requests. That's what your app does best. Everything else, logging infrastructure, metrics collection, security policies, that's what sidecars handle. They take operational complexity off your application's plate. Let me show you what this looks like in practice. On the left, we have container 1, Nginx. This is our application. Its job is crystal clear: serve web traffic. That's the business logic. As a side effect, it writes raw log entries to a file called access.log. Simple output, nothing fancy. On the right, container 2, the log reader sidecar. This container has a completely different focus: operational complexity. It reads that log file, parses the entries, buffers them for efficiency, and forwards them to your centralized logging system. Maybe Elasticsearch, maybe Splunk, maybe CloudWatch. Notice the separation here. Nginx doesn't know anything about Elasticsearch authentication, retry logic, or buffering strategies. The log reader doesn't know anything about serving HTTP requests. Each container does one job, and they collaborate through a shared volume, the crucial link that makes this pattern work. Now let's see how we define this in Kubernetes using YAML. At the top, we declare this is a pod resource. Remember, a pod is the smallest unit in Kubernetes, and it can contain multiple containers that need to work together. Look at the volume section. We're creating something called shared logs using emptyDir. This is temporary storage that exists only while the pod is running. When the pod gets deleted, this storage disappears. It's perfect for sharing transient data between containers. Below that, we define our containers. First is Nginx, our application container. Second is the BusyBox-based log reader, our sidecar. Each one mounts that shared logs volume, but at different paths. This is your blueprint. Copy, paste, and apply with kubectl apply def, and Kubernetes brings this entire pattern to life. This is the concept that makes everything work, the shared volume. Look at this visual. We have one piece of storage, the emptyDir volume, represented by that disk in the center. Both containers connect to it, but through different mount points. Nginx mounts the volume at var log Nginx. That's where Nginx naturally writes its logs. The log reader mounts that exact same volume at /logs, a completely different path. Here's the key insight: different paths, same storage. Think of it like two doors opening into the same room. You enter from different doorways, but you're looking at the same space, the same files. When Nginx writes to /log/nginx access.log, the log reader immediately sees it at /log/access.log. They're literally the same file, just accessed through different mount points. This is how Kubernetes enables true container collaboration. Now, let's see this in action. First, we'll verify our pod is running with kubectl get pods. Both containers should show as ready. Then we'll generate some traffic. We'll exec into the Nginx container and use curl to hit localhost, simulating a user request. Since both containers share the same network namespace, localhost works perfectly. We'll start with a single request, then send 5 requests in rapid succession using a simple for loop. After generating traffic, we'll check the sidecar's logs using kubectl logs with the -c log reader flag. Every single request appears in real time. No delay, no network calls between containers, no complex messaging, just simple file system access to shared storage. The sidecar runs tail-f on the access.log file, so it sees writes instantly and outputs them. To verify both containers see the same files, we'll list the contents of Nginx's directory at /vog/nginx. You'll see access.log and error.log. Different mount paths, same underlying storage. Let's step back and understand why the pod construct is so powerful. First, guaranteed colocation. When you put containers in a pod, Kubernetes guarantees they're always scheduled on the same node. They cannot be split across different machines. This is critical when containers need low latency, high-speed collaboration. Second, unified lifecycle. These containers are treated as a single atomic unit. They start together, run together, and stop together. If the pod restarts, both containers restart. They're bound together for their entire lifecycle. Third, clear separation of concerns. Look at this diagram. The main app focuses purely on business logic. The sidecar handles all operational complexity, reading, processing, and shipping logs. This is the Kubernetes philosophy in action. Compose sophisticated functionality from simple single-purpose building blocks. The main takeaway? The sidecar pattern enforces separation of concerns for operational tasks in Kubernetes.